Okay, here's the current through a 1 millifarad capacitor. I want to sketch the voltage across the capacitor. We're given that the voltage at t equals 0 is 0. There's no energy initially stored in the capacitor. The capacitor is said to be relaxed. We can do this a few different ways. So I of t is equal to c dv of t by dt. So what we're really given here is the slope. So this slope is 1 amp. So dV by dt is equal to 1 amp over 1 millifarad. So 1 times 10 to the minus 3 farads. So the slope is 1,000 volts per second. So that means that this curve between times 0 and 1 starts out at 0 because of my initial condition here. It'll go up linearly with a constant slope that's 1,000 volts per second. If I plot this in milliseconds, at 1 millisecond I'll be at 1 volt. Now down here I have the same slope just with the opposite sign. It'll go back down at the same rate until it gets to 2 seconds and then it'll stay at 0. You can also look at this as an integration problem. The voltage across a capacitor is 1 over c times the integral from t0 to t of the current through the capacitor plus the voltage at this initial time t0. So what I'm doing is actually integrating up to a time t, so I'm finding the area under this curve. If I integrate a constant value, I get a straight line. Since we start out at v of t0, so v at 0 is equal to 0 volts, again per the given initial condition, then for t between 0 and 1, v of t will be 0 plus 1,000. 1 over 1 times 10 to the minus third is 1,000. Integral from 0 to t of 1 dt. So this, again, just increases at a constant rate when t is equal to 1 times 10 to the minus third seconds. This total integral is 1, so I get to 1 volt here. Now that gives me the initial value for t equals 1. So from time 1 to 2 seconds, v of t is 1, this initial value, plus 1,000, integral from 1 to t of negative 1 dt, and this just goes back down until we get to 2 milliseconds. This is 1 millisecond. The answer is the same. It just depends on whether you want to look at it as a slope or as an area under a curve.